Homework 3.2, Polynomial Functions, Video 6. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. The remaining videos in this series will directly associate with questions 10, 11, 12, 13, and 14 in the homework. All right, let's graph these things. Let's put it all together. Now, throughout these videos, I've used 7 different functions. They happen to be written on the sideboard over here in case I forgot. And so we've already done a lot of the analysis for these functions that would be required. Now in the homework, when you're doing one of these problems, chances are it's a function you haven't dealt with yet. So you would have to discover and calculate all of these things. But we've already located in behavior and x-intercepts and the behaviors on the x-axis for all of these. So I'm not going to be recalculating them, but rather I'm going to summarize them. So if you're watching this video and haven't watched previous videos, the answer to where did some of these things come from lie in previous videos. So you may want to go check them out if you haven't already. Well, one function we were using was f of x equals x to the third power plus 5x squared minus 4x minus 20. And we had determined its in behavior, in a nutshell, because the leading coefficient is positive, that means that the right rises. And because the degree is odd, that means opposite ends, so the left falls. But that's the end behavior that we had determined previously. Now, one thing we haven't talked about in any of the prior videos, except briefly in the first, is the maximum number of turns a graph can have. The maximum number of turns is the degree minus 1. This is a third degree polynomial, so 3 minus 1 is 2, which means this graph could turn twice. The rule for what about turning less is if it turns less, then it loses 2 turns at a time. So for example, if something can turn twice, then it could lose 2 of those turns and turn no time, so it could just go up. Or if something could turn 5 times, then it can do that, or you lose them in pairs. So it could turn 5 times, or it could turn 3 times, or it can turn 1 time. But this graph can turn either twice or none. Odd, even, or neither, and symmetrical implications. Now this we'll have to do because we haven't done them in previous videos in this series. But just a reminder that odd, even, or neither starts by checking what happens when you put in a negative. And to make this discussion a little faster, odd powers keep negatives, even powers lose negatives. So for example, if I put a negative here, raising it to the third power will keep it negative. But if I put a negative here, raising it to an even power will make the negative go away, so this will stay the same. Putting a negative here times a negative will make it positive, and then there's no x here, so that stays the same. And then we compare this to the original function, and we compare it to the opposite of the original function. And it's easy to compare to the original. Does this match that? No. And what that means is that there's no x-axis symmetry. Actually, that should say y-axis symmetry. No function will have x-axis symmetry. Well, there's one, and one of you emailed me what it was. Nice job. Is this the opposite of the original function? Well, we can check that out real quick by asking, are all the terms opposite what they used to be? This one is, and so is this one, but those aren't. So it's not the opposite of the original function. It's not an odd function, so there's no origin symmetry. And in your homework on these questions, there will be a part that asks you, is this odd, even, or neither? I get the homework printed out right here. And which symmetry does that imply? That's the way you check it. If you have to guess at it, you can, but I believe you only get one shot at answering it. So this is neither, which means it has neither y-axis symmetry, we can't fold it across the y-axis, and it doesn't have origin symmetry, meaning that we can't turn it upside, I feel like a little teapot, that we can't turn it upside down and have it match itself. All right, what's the y-intercept? Well, we haven't calculated any y-intercepts, but they're pretty easy. Just put in 0. 0 will kill the first 3 terms and leave a negative 20. So the y-intercept is negative 20. What are the intercepts? Well, we already listed all those, but I'll write them again. I believe they were negative 5, 2, and negative 2. And let me check something real quick on this homework question. It actually, on this question, it doesn't actually ask you the multiplicity, it just asks you cross or touch, which is a consequence of the multiplicity being odd or even, but all of these had an odd multiplicity, which means it crosses, crosses, and crosses. And now we're going to put it all together. To put it all together, what I would recommend doing is starting with a blank graph, a blank coordinate plane, if you will. And for the end behavior, putting arrows as reminders, not that you're going to connect, but for example, the left falls, so I'm going to put an arrow pointing down over here, but the right rises, so I'm going to put an arrow pointing up over here. Now, I'm not saying I'm going to connect these arrows, they're just reminding me what directions the ends need to point. As far as the maximum number of turns, don't worry about that until you actually sketch it. Really, you should jump to the intercepts. There's a y-intercept way down here at negative 20. I'm not going to mark it all off. I'm just going to put a negative 20 with a dot down there. As far as the x-intercepts, there were 3 of them. Now, these are small, so I'm going to mark it off. There was an x-intercept at negative 5, an x-intercept at negative 2, and an x-intercept at positive 2. Now, to summarize the behavior on the x-axis, cross, 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 I'm just going to put C a bit above each one. When we have one that touches and turns, I'll put TT. All right, so here's what I need to do. I need to start low, cross, cross, hit this point, cross, and end up high. Do you see where the graph's going to be? I need to start low, so this looks like a good point. Cross. Now, here's where we reach our limitations as an algebra class. In order to cross here, it's going to have to turn around. A natural question is, when will it turn around? And when it turns around, how high will it be? You know, kind of like a vertex on a parabola. But in order to answer both of those questions, we need to do calculus, and this is in a calculus class. So, if you're sketching these by hand, don't worry about how high or low it goes before it turns around. Just turn around somewhere so that you cross where you're supposed to. I do know that I have to dip down and touch this. That doesn't mean it's going to be where it turns around. It might go lower and then turn around. I really don't know without more evidence. But in order to capture everything that we've drawn, I just need to touch it at some point and then come back and cross here, and I'm ending in the correct direction. So the game of connect the dots is actually pretty easy if you know where to start, where to cross, touch, and turn, and where to end. We're going to do the same thing for the other 6 functions that we've seen. So before you move on to the next video and the next video, the next 6 videos, so this is going to end up having 12 videos total, are all going to be the same thing with all the functions that we've seen. So, and they're going to be in alphabetical order, F, G, H, J, P, Q, and R. So if you're up for the challenge, go pick any of those functions and see if you can do the same thing with it. And then watch the video and see if you get the same graph. But I'm going to do short videos for all of them. If you get it, you can stop watching the videos, but I would recommend checking them out.